All right. What did we do last time? So last time, we talked about kind of forward kinematics-y stuff, which I did only like a very cursory, look at just to calibrate us. And then we talked about differentiating quaternions, which is kind of what you need. I should mention this is only one way to do this. There are lots of ways to do this. You don't have to use quaternions. You can use like rotation matrices. There's like, and especially in the kinematics world, actually, people are quite into the Lie group stuff. So you maybe have heard of like the product of exponentials, for doing forward kinematics. It's the same stuff. Like that's just being a little bit more explicit about all the Lie group stuff and SE3 stuff. I like using quaternions because I think they're straightforward, and this is actually what people use in software and simulators and in computer graphics and stuff. So I think it's they're a little nicer computationally, but there are, you will see other things for sure. And I'm only kind of giving you like the very, very little teaser version of this stuff, the kinematic stuff, for the purposes of like bootstrapping what we're going to talk about for dynamics. And I'm kind of assuming you've seen this before, and I'm just doing it to like ground notation and stuff and like lower view. Okay, so that was last time. Today, I want to do, we'll do like a quick review of this kinematic story in 3D with floating base stuff. And that's sort of the full story with the quaternions that we were getting to last time. And then we kind of had this little side trip through quaternion math. So I'm going to we'll rehash the 3D case with the floating base and with the quaternions in there. And we'll go through how to differentiate it with the quaternion tricks from last time and how to get your, the velocities you want, right? Basically like the V and omega, the like position derivative, normal thing, but then the omega instead of like a quaternion derivative, right? That's kind of why we have those tricks. So then you can write your kinetic energy, your Lagrangian, and then we're like sort of good to go. So we're going to do that. And then we're going to start talking about how you do rigid body dynamics, like Euler's equation, but then like generalize that to floating things with arms and such, right? Where you have this floating base that has an attitude representation that's like a quaternion or whatever. So we're going to talk through how to do that, just a little gnarly. It's probably the hardest thing we're doing in the class. So, today might be a little rough. I'm going to try my best to make it less rough for you, but it's the math's annoying. It's just messy algebra. And I don't know, I've tried, there's like several ways I've tried doing this. This is like the best I've come up with. So bear with me. I keep feeling like there should be like a cleaner, simpler way to do it, but I haven't figured it out. So that's what you're getting. The other stuff is messy too. It's not just me. So anyway, so we're gonna do that. Then we're gonna talk about how to do like the least action Euler-Lagrange thing for rigid bodies and kind of why that's weird and different and why you can't get like Euler's equation for a rigid body from the, so you will recall we did like Euler's equation based on some like weird momentum conservation arguments and like rotating frames and didn't get it from a Lagrangian. This is why. So now we're going to get it from a Lagrangian, which is, I feel like something that always bothered me that no one ever did in like any physics classes. They always do all this Lagrangian stuff and like, oh, here's a rigid body. And like, here's this weird angular momentum argument to get the rigid body dynamics. And you don't use like the Lagrangian stuff to get it. You will understand why after the pain of today's derivation, why they don't do that in most even graduate level courses on stuff. So we'll do that. And kind of the core, can anyone like, we kind of mentioned this maybe a little bit when we talked about Lagrangian stuff, like there's a key kind of reason why the standard Euler-Lagrange stuff breaks when you start talking about rigid bodies. Does anyone know why? So the core assumption that you make when you write down the Lagrangian stuff, the Euler-Lagrange equation, and chug through the like calculus of variations tricks to get the Euler-Lagrange equation, one of the key assumptions is that your velocities are your q dots. So you have q and q dot, where you have like your pose variables and your velocity variables, and the velocity variables have to be just the straight up time derivative of your pose variables. And that's what the Euler-Lagrange equation assumes. In the rigid body case, you can't do that because your velocities need to be omegas, and there's no like pose that is equal to, the integral of omega, or said another way, there's no like q's such that q dot equals omega. That doesn't exist, right? So you got Euler angles, quaternions, rotation matrices, whatever you pick for like your pose representation there. you've got something non-trivial and weird mapping omegas into those derivatives, right? And so that's why the Euler-Lagrange equation doesn't work here at a very basic level. And you need to do something fancier. We're going to do the something fancier today, but it's literally just still least action. You write down least action and then you turn the crank. It's just the Euler-Lagrange equation makes that key assumption that we have to break to do this. So it gets messier. Okay, I'll stop talking about it and just do it. And then we're going to do, kind of hopefully, we'll see how far we get on this today. We're going to do like the floating base story in general, which is, kind of the answer at the end of this is like the standard thing that everybody uses for all floating base robots that's under the hood inside of Mujoko and Bullet and stuff like this. The derivation is probably not the way those people would get it, but there's lots of ways. Okay, so just as a kind of rehash of last time and to make sure we're all squared away on this. And this is again like, simplified stuff, and there's lots of ways to do this. So we're going to have like a floating base with, the usual center mass, blah, blah, blah. And then we're going to have, say, like a robot arm attached to this thing with some links and, the little end effector thing. Cool. So the Ford kinematics story for this is not really any different from like the 2D case or the fixed base case. The only difference is that instead of starting out with like, the identity and like whatever, you start out with the pose of the base as like the base link, basically, right? And that can move around. So that's got its own pose. And that's the only difference. Otherwise, this is very straightforward and the same stuff we did yesterday. So I'm just going to write it down quickly, and then we can use it for the dynamic stuff. And I'm assuming you guys have gotten a healthy dose of this kind of stuff from KDC or whatever, somewhere. And there's lots of books that do this stuff and like cover all the other stuff. So like kind of similar to last time, I'm gonna write this down in like cartoony, version. So we have the base, here, and I'll decorate it all up. So that's the rotation from like the base body frame to the inertial frame. And if I write this in terms of the quaternion, we kind of like talked about this earlier on. I'll just kind of quote it here. We're going to end up using this stuff a whole bunch today. So these are like these quaternion multiplication matrices that we define, right? The left multiply, right multiply, and that hat matrix that maps us from like 3D to 4D and stuff like that. So this is just the expression for, I think we did this earlier on in the class. This is how you go from a quaternion Q naught, say, to a rotation matrix. That's the expression. Cool. Yes. Yeah, sorry. This is like notationally terrible. I apologize for like, it's just hard to deconflict all the notation. So this R is the right multiply quaternion thing. This R is like the pose of the link, and the subscripts here indicate which link it is. So the base link is, index 0. And this is like the frames, kind of trying to keep track of that. And then you've got your position, which is in the, so the idea here is this is in your state vector. And this guy also is in your state vector. Like the position and orientation of the base link are just hanging out in the state vector. And I'm just putting them in, I'm just doing this like kinematics-y thing where I'm turning everything into like rotation matrices or whatever you want, really. And so that's the base case. And then we just kind of go from there, just like yesterday. So, or Tuesday. So you kind of bootstrap, and now the next link is the orientation of the previous link times, and so because Qs are typically reserved for like configuration vectors in mechanics, I'm going to use thetas for joint angles. So that's what we're going to try. Notation is really annoying and tricky to get, clear and whatever. So this is like, we kind of did this last time. So now you've got like recursion, and you can kind of go along the links and whatever. And this we defined last time, right? So this is, the position of the last link. This is the vector from the CG of the last link to the next joint. And this rotates that from the body frame into the inertial frame. So I can add it on here. And then this goes from the joint to the CG of the next link. And this rotates that into the inertial frame. And this is just chaining the last body pose through the joint angle rotation. And you kind of just keep track of those on. And the only difference from last time is just that the base case is like as a pose, right? Instead of just being bolted to the world. Okay, cool. Everybody cool with this? You've done this before. Hopefully, I'm just like trying to make sure we're on the same page. And then so we can take this whole thing and like write it down. So you've got some function that computes this, right? Whatever you use, it's all good. And we're just going to say we have some function that does that. So it's just like last time. So in the floating base case, so I'll just write this down. We're assuming we can get the pose. So like position and quaternion, say, could be rotation matrix if you want, whatever. We're going to use quaternions because we have all these tricks for doing differentiation and stuff. So this is full pose, position and quaternion in the world frame position, body to inertial frame rotation for every single link. And we're going to say this is some little function little k of q, where q is the configuration vector. And to be super clear about this, in this floating base case, we're going to assume we've got the base link pose in there, and then all the joint angles. So theta 1 through theta n. Cool. And this is configuration. Lowercase k, right? Sure that's clear. Okay, all good. Same stuff as last time. Don't screw up. All good. Okay. So next, what we're going to do is talk about this whole kinematic Jacobian thing, which we kind of teased last time, and I'll do it for this case specifically this time. So this is how you get the velocities, right? And specifically, if I naively diff this, the reason we're talking about all this stuff is if I naively differentiate this thing, on the right-hand side, I'm going to get q dot, which has a quaternion derivative in it, like a q naught dot, which is not what I want. I want omega, right? And then on the left-hand side, I'm going to get a bunch of q dots for like the quaternion derivatives of every link, which is not what I want either. I want omegas, right? So what we're doing now is literally just sort of smooshing this thing on both sides with the Jacobian we need to like map those q dots into omegas. So we get the thing we want. And then that smushed version, we're going to call the kinematic Jacobian. That's like the thing you expect. It's going to map like a V into a, velocity thing on the other side. Cool. So what we want out of this is say R naught dot omega naught, R1 dot omega 1 dot 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 Rn dot omega n. So we want that. And in order to get that, I'm going to take the like partial k, partial q Jacobian of this guy, which has all these quaternion derivatives in it. I'm going to apply like the attitude Jacobian stuff in the right spots to get that to work out. And so we talked about this last time, right? It's also just the quaternion kinematics, the mapping like q dot into omega that we talked about when we talked about rigid body dynamics. That's the other way to look at it in this case. So we're going to end up with like a 2G transpose in all the spots on the output side corresponding to the rotation stuff. So there's that. Then we've got our sort of the normal Jacobian that you would take of that kinematics function. And then on the input side, we just have to do this in the spot corresponding to Q naught. So that just looks like, I, and we got a 1/2 G of Q naught in here, and then identities the rest of the way down. And this is going to multiply the sort of the V that we actually want to have. That being So then we're going to have in here the r dot naught, omega naught, and then all the joint angle derivatives. So we've got to label this stuff then. This whole thing where we've sandwiched the sort of naive Jacobian of this kinematics function on both sides with the additive Jacobian stuff. This whole thing we're going to call big K of Q, the kinematic Jacobian, and then the thing over here that is sort of the base velocity stuff plus all the angle velocities, we're going to call this V. Cool. So to be super pedantic, right? The key thing here is that V is not equal to Q dot, right? Q dot has a quaternion derivative in it. V has omega in it, which is the thing we're used to and the thing we actually want, right? So that's kind of the reason all this is annoying and hard compared to like normal Euler-Lagrange stuff or fixed base stuff, right? In fixed base case, this just has theta in it, theta dots, and then that's fine, and that's Q dot. In the floating base case, we have to deal with the quaternion weirdness or attitude, general attitude weirdness in the velocity. So kind of this V is the same for no matter what attitude representation you use, right? If I use Euler angles, rotation matrix, whatever, the V still has an omega in it, right? So what would change is this guy also is the same no matter what, right? The only thing that's different, this is kind of worth mentioning, right? So the only thing that's different is inside here, I'm going to have like rotation matrix, Euler angle stuff, whatever. So this guy will change. It turns out that up to a constant scalar, the attitude Jacobian thing stays the same, which is kind of interesting. So I guess the message here is the input and output of this guy stay the same no matter what attitude representation we use. And what ends up changing is inside this K, how you compute this K, like the details of these guys will change. But when you smush it all together, this guy is like coordinate invariant in some sense, which is nice and seems like in a deep sense, right, I guess, right? So this is like kind of the right thing to do. Okay, enough of that. So, okay, some notes. This is really at the heart of like why we can't use normal Euler-Lagrange things, is that V doesn't equal Q dot here. And then the last thing we should talk about is sort of the mass matrix and like kinetic energy story, which should be no surprise from last time. So we can write down kinetic energy. It's just the sum over all the links. So we get, 1/2 mv squared. So this is r dot. This is K. And then we've got the angular part. And this just equals, like we talked about last time. So all we need to do, I can stack up all the r dots and omegas into this guy here. And I'm going to use this Jacobian to write it in terms of this V, the sort of like joint space V or whatever you want to call it. So that whole thing looks like V transpose big K of Q transpose this M bar K of Q V. And then we call the whole thing in here with the kinematic Jacobians in it. This is M of Q that we're sort of used to dealing with when we talk about mass matrix for these things. And this M bar, like we talked about last time, this is a constant matrix that has all the masses and inertias of all the links. Okay, so this is stuff we talked about last time for the most part. This is just doing it out one more time with all the kind of, in the floating base general 3D case. Any questions about this? So you guys have done this before, I assume. Who has not seen this before? Okay. Have you guys, so you guys, I'm assuming, just haven't taken KDC, right? So I think this is, at least some version of this is covered in, that's the K in KDC, I hope. I'm not sure exactly what goes on in there, but I assume this is like something that gets talked about in some form. Okay, cool. Any questions about this? It's a straightforward idea though, right? It's like a lot of bookkeeping to like, but you work your way down the links. You kind of apply the rotation for each joint angle, but in 3D, right? Chain those together so you get the global rotation from like the link frame to the world frame for each link. And also you add up the translations. So you get the position. So you get the full pose, position, and orientation of each link. I do these weird quaternion tricks to diff that. And like, so I can get the linear and angular velocities like I'm used to for this guy. And that's this kinematic Jacobian thing. And then I can use that to get my mass matrix from like in the straightforward way, just from the definition of kinetic energy. Right? Yeah. No. Yeah, this is why this is annoying. So omega from like, you know, when we've talked about this in the past, right? So you have this q dot equals 1/2 q times omega hat, where that's like this is the kinematics for a quaternion, right? So we did this when we did rigid body. So I'll write this like maybe more carefully. Like that's the quaternion kinematics. So I can shuffle this around and write omega equals 2 q dagger, which is like the quaternion transpose kind of thing, right? Q dot. So that's super obviously omega does not equal q dot, right? And really this is what's buried in the output side. So this says q dagger times, that's 2 like L transpose of q times q dot, right? And then I got the hat thing. Oh yeah, there's a hat matrix over here because I got to go from 4D to 3D, right? So this is really 2H, and this thing, this is the additive Jacobian, and that's what shows up in that left-hand side matrix, right? So it's literally just those kinematic Jacobian things, like the matrices sandwiching on both sides are really just the quaternion kinematics. So this is the left one that's going from q dot to omega, you know, all the red spots on the left. This is the right one that's going from omega to q dot on the right-hand side. That's where you get the 1/2. Like this whole thing is 1/2 G, right? And this is 2 G transpose. That makes sense? Cool. Maybe that was like an easier way to explain that, and I should have done it that way from the beginning. Let's like move this over. Maybe that's a useful aside. And yeah, so this is 1/2 G of Q omega, and this is 2 G of Q transpose Q dot. So that's literally all I do, right? That's like literally just doing that impedance matching between omega and Q dot on both sides of the matrix, right? Okay, cool. Next, are we good? Yeah. All right. So a brief aside on like floating base systems and like why we care about this. So this is like literally anything that isn't bolted to the ground, like old school industrial manipulator. So this is in robotics. So this would be, you know, mobile, legged, aerial, underwater, and like space robots. So anything that has legs, wheels, flies, swims, or is in space is like, you know, kind of where the floating base thing happens. Anything that isn't like bolted down in a factory. And like kind of at a high level, what we're trying to do here is we talked about like all this SE3 rigid body stuff and Euler's equation, right? At one point in the class, and we talked about these special Lie group integrators and all this kind of stuff, right? But we didn't use any Lagrangian stuff to get there for the most part, right? We want to be able to, then we talked about all this Lagrangian stuff for like fixed base systems with joint angles, right? And all this stuff. What we want to do now is basically bolt those ideas together. So we want to combine the SE3 stuff for the base with all the Lagrangian stuff for the joint angles, right? For the legs or arms or whatever you've got attached to your floating base. That's kind of the big picture thing. So that's kind of high level. And then what we're going to do to kind of ease us into this, it gets gnarly. We're going to do the single rigid body again, but this time from like a least action Lagrangian perspective, which we didn't do last time. And that basically, if you can do that, then you can bootstrap the rest, and like handling the joint angle part is easy. It's like the same. But the base length case, the floating base length case, makes this all complicated and hard. So we're going to just do that, and then the rest follows very easily. And we'll try to make it as painless as possible. Has anyone done this or seen this before? Okay, so let's do it. So let's see, this is the so-called free rigid body. So when I say free rigid body, I mean no external forces, no potential, right? Just like tumbling asteroid or satellite or whatever, floating in space, no gravity, nothing, right? No other forces. So what's the Lagrangian for that? It's the Lagrangian for this. It's just the kinetic energy, right? So it's if we're talking about both, if full pose, right, position and orientation, it's this, or I should, yeah, I'm getting my notation kind of mixed up. So we've got like a position derivative, right? So it's worth mentioning at this point, this Lagrangian is sort of like separable. What I mean by that is, if I were to write down the full mass matrix for this thing in all 6 degrees of freedom, it's block diagonal. So there's no cross coupling between the position stuff and the orientation stuff, right? Does that make sense to everybody? So because of that, totally separable. And I can do the position dynamics, which just ends up being F equals ma, totally separate from the rotation dynamics, which ends up being the Euler rigid body equation. There's like another way of thinking about that, right? In the beginning of the class, we did Newton-Euler dynamics for like quadrotors and stuff, and I just wrote it down. It's like, yeah, it's just F equals ma, and then this Euler equation thing. At a deeper level, this is kind of why you can separate those, because there's no cross coupling in here, right? There might be cross coupling, through the forces. So you could write down a potential that cross couples, and then this wouldn't necessarily, it would show up on the force side probably, right? But right here, because this guy separates out like that cleanly, there's no, like another way of thinking about it is, if you think of mass, like you can think of that as like a density function, almost like a probability density, like a covariance. They're not correlated, right? They're sort of like no cross coupling terms in the mass matrix. So you could do this separately. So let's look at just the attitude stuff. What would this look like if I tried to do the Euler-Lagrange equation thing to this? Like, think about that for a second. So it might look something like, I don't know. So it's ddt partial L partial Q dot, right? So maybe we think, maybe omega is like a Q dot type thing. So maybe we can do this. And there's no Q in there. So it's just this term, right? So what does this look like? This is just J omega dot. And like the Euler-Lagrange equation says that's it, right? If I sort of like try to do this, which makes no sense. There's not that omega cross J omega like term that we know should be there from the Euler equation, right? So that's clearly wrong. And that's sort of, again, the fact that omega does not equal Q dot. And this is kind of showing you that Euler-Lagrange thing does not work. Okay, and yeah, okay, so we know the right answer. So this is going to be a frustrating exercise in getting an answer we already know via a different path that is a lot more work. That's why we didn't do it this way the first time. Okay. So yeah, and then yeah, the standard Euler-Lagrange equation doesn't work here because omega doesn't equal q dot for any q dot, right? All right. So the way forward here is to go back to the least action principle, which always works, and just write that down properly. And what we're going to do in this case is we're going to write down this kinetic energy, that Lagrangian, which is the right Lagrangian. But we got to figure out, like, somehow in here, we got to map q's and q dots into omegas. So sort of the obvious thing that we're going to do is tack on the quaternion kinematics as a constraint, as a kinematic constraint. So let's write that down. And then it's just turning the crank and doing the same stuff with the constraint term in there. But there's some interesting little nuggets along the way that I will point out to you. But that's the key idea. So if you know how to do this and you know how to do the math, you can sit down and just work it out. And the rest of this will be painful. Okay, so here's what that looks like then. So we're going to do like min over both the, the pose trajectory and the velocity trajectory. So the deal here is, right, we've just basically said, v doesn't equal q dot. So I'm going to write this in terms of the v's and q's I like, and then I'm going to add a constraint saying how v is related to the q dots, right? That's it. So I got this. And we'll just do the rotation part because we can split them apart, like we said, subject to this quaternion kinematic stuff that I kind of just wrote down. Here it is again. Or equivalently, you can write it this way, the other direction. We're going to write it this direction. Cool. So that's the same stuff that showed up in those big Jacobians up there, just the kinematics between these guys. That's now a constraint. So with that, I can write down the first order necessary conditions, aka Lagrangian stuff in the optimization sense, right? Where I'm going to take the constraint, put a Lagrange multiplier on it, and stick it upstairs in the objective function. And there's something fun that happens here that I don't know if we've talked about yet. Okay, so what we're going to do, like, this is a little bit cartoony, abusive notation here. So, but hopefully you get the idea. So we got this thing, the derivatives of this thing with respect to everything. And these are like the variational derivatives, which we'll kind of do out in detail in a sec. And then we've got, there's 1/2 here, kinetic energy thing, Lagrangian thing, and then plus this new Lagrange multiplier term. I'm going to call this Lagrange multiplier L. And then this is 2H transpose Q dagger times Q dot equals omega, right? So I'm going to write that down like this, minus omega equals 0. And that's how we do this Lagrange multiplier stuff. So this guy's derivatives, right? This guy's variational derivatives with respect to both Q and omega has to equal 0. And you can kind of like guess at where this is going. Basically, we know from before, like this term spits out like a j omega dot, right? This stuff is going to end up spitting out that omega cross j omega term from Euler's equation. It's coming from like this constraint. It's telling you how to glue together the, the pose stuff with the velocity stuff, right? So some notes, this setup where I like have this kinematics constraint, this is called the Euler, or the Lagrange-Pontryagin principle, which is like a long mouthful thing. And the reason the Pontryagins in there is this looks exactly like an optimal control problem. This kinematic constraint that says, Q dot equals whatever, looks exactly like when I have x dot equals f of xu dynamics constraint tacked on an optimal control problem. So it turns out that the first order necessary conditions for this look exactly like the Pontryagin minimum principle from optimal control. Fun fact, I don't know. Okay, so that, so this is, yeah, what is this? This is like It's a weird thing. So this idea is, I think, is called Lagrange-Pontryagin, and then like the first order necessary conditions we're going to get at the end are called the Euler-Poincare equations, because they're like generalizing the Euler equations to like Lie groups, and like Hess Poincare did that first or something. So these all have like lots of people's names attached to them and whatever, but yeah, I don't care. Okay, so here we go. This thing, the Lagrange multiplier, associated with the kinematics constraint. And I set this up in a very particular way to show you something cool. So I showed you I could write that constraint a couple ways, right? And I could also like order this a couple different ways inside here. This particular choice, though, is kind of the right one to make for the following reason. So if I go and start taking those derivatives, let's do the omega one first because it's easy. So remember, omega is just a vector. That's all good. I can just take a normal derivative and nothing weird happens. So let's do that one first. And see what comes out. Okay, so I'm going to use this weirdo notation that's sort of the variational calculus. Like this is variation with respect to omega of S of the action. And then I'm going to write this down. So we got this guy. And then I'm going to sort of diff inside the integral. So here's like delta omega, right? So like this, we talked about this way back in the beginning. We did calculus variations. Like if I wanted like partial S, partial omega, I'd have to like, divide through by the delta omega, which is sort of not, it's kind of weird in this context. We're not going to do that. These are all trajectories that are functions of time, blah, blah, blah. But you'll see we've done this before. Okay, and then the Lagrange multiplier term, I get, I'm diffing with respect to this omega. So I get minus L transpose delta omega. dt, this thing has to equal 0 for all delta omega, right? That's like how this works. So then I go look inside here. I don't have to do any weird tricks here with like the integration by parts or anything. This is all nice. You just pull the delta omega out, and what's left is this, omega transpose J minus L transpose has to equal 0 all the time for this to hold, right? So that tells us that L equals J omega. What's L? Angular momentum. That's cool. So this is a general thing. If you do this like Pontryagin thing where you put your kinematics in as like a constraint, the Lagrange multiplier of your kinematics constraint, aka the mapping between your like velocity variables and your pose derivatives, whatever that is, right? Even in the trivial case where you have like v equals q dot, if I do it that way and write this down as a constraint, the multiplier associated with that constraint is the momentum, is always the momentum. And there's sort of some deep stuff going on there. This is again related to like when we talked about the Hamiltonian stuff and the dual problem, right? This kind of popped out, right? Same story. That's a general thing. Okay, fun. Okay, so now that gets nasty. So now we got to do is take the q derivative of that guy, right? This is horrible. Apologies in advance. We'll make it hopefully less painful. Maybe I'll try to like sketch some of the stuff without going into the like super gory details. Okay, so high level, we need to go through that thing and differ with respect to q. It's super annoying. We're going to use all the quaternion derivative tricks, and we got to like kind of do a bunch of chain ruling and stuff, and we've got to worry about like dipping through the dot on that guy and the dagger on the other one, which is annoying. So I'm going to give you like all of the notation stuff that you need for this, and then we'll kind of like quickly, hopefully, sketch this out. Okay, so here's all the things you need. So we got, okay, so just the velocity stuff. So in there, right, I have this term that says q dagger times q dot, right? I got to diff that term. So I'm going to write that out and I'll show you like how to get the sort of proper derivatives of all the pieces. So this thing equals L of q transpose times q dot And then I can also write it the other way as R of Q dot times Q dagger. That equals, I'm going to write this. I don't know if we did this one before, but this dagger, remember, what does that do? That flips the sign on the vector part of the quaternion, right? I can write that operation down as a matrix also. So I'm going to introduce a matrix called T to do that. And that is simply like this 4x4 guy with a minus identity block in the bottom corner to flip the sign on the vector part, right? Cool. So that's that term. Now we have to diff this stuff. So these are like all the ways I can write this down, right? And the reason I do this is like if I want, for example, partial of this thing with respect to Q, it's that. Okay, you get the idea, right? If I want partial of it with respect to Q dot, it's that guy. That's why we do this, right? Okay, so this is where it's going. Okay, so here's, let's do this. So we've got this sort of like, you know, derivative of Q thing is equal to 1/2 attitude Jacobian of Q times like this little delta phi guy, right? So I'm converting this from like a, you know, Q derivative to a phi derivative. And in this case, you could think about, right, if I like want the Jacobian of this guy, this is like dq dphi. I like sort of divide through is this guy, right? That's sort of one way to think about it. And this, you know, just the definitions, which maybe will be important in a sec. This is just this. Okay, so I can take that. I can then like start plugging it into the things I actually need up above. So up in that expression, I have a Q dagger. So I need this for the Q dagger. So there we just use that T matrix. So this is equal to T delta Q. And then if I sort of like expand that out, it's 1/2 T L of Q H delta phi. I'll expand it out, right? So now that's like the full thing for the Q dagger term. I also need this for Q dot for the other one. So how we do that is I'm going to go, so I want delta Q dot. I'm just going to take the expression for delta Q and differentiate with respect to time. So you get this product rule thing. So I'm going to get a G of Q dot times delta phi, and then a G of Q times a delta phi dot. That's how that works out. Yeah, so I guess we'll write it this way. And I can expand that out with the like definitions of G too, if I want to. I guess we'll do that. Okay, so there's that. Now I take all this crap and plug it in upstairs where I've got to take that derivative in the Lagrange up there, right? And I take the derivatives. I do a bunch of algebra and like massage this around. And at the end, out pops Euler's equation. That's the punchline. So you know where we're headed. If the algebra is like just super messy. So maybe I'll put it all in there and we'll take a look at it real quick. And I'll maybe hopefully it'll just like give you some hints and sketch out. If you really care about this, you should just do it yourself, honestly. But you know, it's not that fun when I do it in front of you. So if we put this all together, I get something that looks like, so I'm going to do this like, you know, variational derivative with respect to Q of the action. And if we go back and like look at the action up here, again, just as like a refresher, it's that guy up top. The first term doesn't have any Q stuff in it. So the first term goes away, right? Its derivative is 0. And the second term has this Q dagger times Q dot stuff in it, which I just wrote out how to take all those derivatives. I'm just going to plug this in the right spots up there. And it's Q dagger times Q dot. So it's a product rule thing, right? So you understand how this is going to work out. So I'm going to just like sketch this really quickly. So L transpose times 2H transpose, and then you end up with like delta Q dagger times Q dot plus Q dagger times delta Q dot. And then I can go sort of expand those out a little bit. There's some nice things that happen, and there's some really ugly things that happen. In general, it's just very ugly and lots of algebra. So I'll write out like one more step of this maybe, and then try to like give you the highlight reel. So there's our delta phi thing. And then we get this thing. Yes, like maybe I'll write this down. And then down here, last term looks like. Okay, that's a mess. Okay, so this thing, so there's a couple of nice things that happen. This thing, like that's like L transpose L business happening here. What can we say about that? It's an identity because L is an orthogonal matrix. Okay, so this thing drops out. This whole thing actually just drops out. With the H's on there too, it becomes a 3x3 identity. So it's just this delta phi dot thing. That's kind of fun. So maybe we'll write another line out of this thing, and then I'll hopefully cut to the chase and not belabor it too much. So T naught, T final. You've got this L transpose delta phi dot from that term that I just said, does the identity thing, and that's cool. And then I get another really big nasty term that has a lot of these things in it. Looks sort of like this. And then I'm going to do a little hand waving here and explain to you what happens without actually like doing all the gory details. Okay, so here's like the next move or two. Okay, so what are we going to do with this guy? Oh, did that not show up? I hate it. It was going so well. So the first term there was L transpose delta phi dot. What do we think we're going to do with that? Hey, we're back. That was relatively painless. Okay, first term, what's going to happen there? So remember, the game is I want to write everything in terms of like delta phis, and then pull that to the side. And the argument is it has to be true for any delta phi. So the thing in the bracket on the left has to equal 0. That's what we just did before, right? Same game here. And we've seen this particular move before, which is why I'm asking. So here's the phi stuff. That's cool. Here's a phi dot. I don't like that. What do I do over here? I do integration by parts. What is the punchline story there? What happens when I do that? Yeah, so you flip the dot. The heuristic, remember this in your brain thing, if you do this a lot, you flip the dot and you pick up a minus sign and a boundary term that always goes to 0, because if it doesn't, we're in trouble and we've done something completely wrong. So this turns into L dot transpose delta phi, and then like, I got everything in terms of delta phi, and then this whole thing just has to equal 0. So that's the move. So what's L dot? J omega dot, right? So that's the first part of the Euler equation. This big, nasty horribleness, you know what's going to happen. It's going to turn into omega cross J omega. How you get there is not actually that bad. I'm going to give you like the, pretend hand wavy story. So this looks like, so it's got a hat on it, and it's like a Q dagger, right, times Q dot situation. What does that look like? Q dagger times Q dot is up here. Looks like this, right? So this is showing up in there. That's omega. right? In particular, this is the hand wavy part. You can write this out. It's not hard. But it's just a lot of annoying algebra. So this is like this H transpose Q dagger Q dot term. That's an omega thing, right? The key difference is the Q dot is buried inside this like left quaternion multiply guy. So, and it's got a bunch of hat stuff on it. So the hat stuff is really saying that we only care about the vector part, right? It's getting rid of the scalar part. Okay, so do we remember what the quaternion multiplication thing looks like if it's a pure scalar? Can you remember?
Pure scalar.
Or pure vector, I'm sorry. It's I times the scalar part.
Oh yeah.
The top row goes away, right? The H's get rid of the whole top row. The scalar part we don't care about. We're only keeping track of the vector part term on the bottom. What does that look like? It's a cross product, right? Okay, so this thing, what does this thing actually say? If I actually like work this all out, I turn this into an omega, and it's buried inside this bottom thing. What do we get? You get an omega cross, and it's specifically, you can write it down as like an omega hat, cross product matrix guy, and it's got a 1/2 on it from the fact that the real omega has got a 2 on it. Okay, so this is a 1/2 omega cross thing. It turns out if you stare at this one, similarly, this ends up being a 1/2 omega cross thing. The whole thing ends up being like an L transpose omega cross thing. When I transpose it all, it ends up being minus omega cross L and minus L dot equals 0. So the whole thing ends up collapsing down into L dot plus omega cross L equals 0. That's Euler's equation. The really, really gory part that I'm going to spare you is actually just expanding these matrices out and realizing that it turns out that it's just the bottom chunk with just the omega in it that ends up being an omega cross thing. Okay, so that's what happens. It's just really long and annoying. I don't know a better way to do this. There's other ways, but they're all really ugly. And this is like kind of consistent with the stuff we've done. So I'll like write down the hand wavy stuff for you. So this turns into L dot transpose delta phi. And then this whole mess, if you expand it out and kind of keep track of everything, turns into omega hat, where hat is the cross product, skew symmetric cross product matrix. And we talked about this before, right? Everyone's seen this before. Also known as the little SO3 Lie algebra of rotations. Okay, cool. Super ugly. I hand waved a lot of that. Hopefully you don't mind too much. It wouldn't have been very much fun to spend the next 10 minutes doing it, I promise. Okay. Yeah, so this ends up being a minus sign on it, you're right. And then it turns out, so this looks like L transpose omega hat. When I flip it around, when I flip the order of a cross product, I pick up a minus sign, right? So when I flip that and I turn into omega cross L, I pick up another minus sign, and then the signs work out. And then the whole thing ends up being the Euler equation. So actually, if I like, and let's write down. This is integration by parts. This is like just expanding out that whole mess of matrix identities and stuff. So at the end of this, you get like this thing equals delta phi transpose L dot plus omega cross L dt equals 0 for all delta phi. And then you say, okay, cool. This means L dot plus omega cross L equals 0. And if I plug in the definition of L from above, I get the Euler equation that I was after. So, I don't know, a little hand wavy. Hopefully this is the right balance of hand wavy versus pain. Okay, so things to say about this. I kind of like threw out these French names and stuff before. This thing is this Lagrangian thing. This is the Euler equation. We got it from Lagrangian playing those tricks. It turns out you can do this in general for any Lie group. I did it for the specific case of SO3 here. The general case of this equation for any Lie group, if I generalize it to arbitrary Lie group, is called the Euler-Poincare equation. So it's the generalization of Euler's equation to a Lie group. All Lie groups have that same kind of structural property of like the kinematics kind of have that flavor, right? And the velocities don't equal the q dots or whatever. So that's worth knowing about. And it looks basically exactly like this in general. So for any Lie group, turns out this omega cross thing, we talked about how that's the little SO3. This thing's called like the adjoint, like that AD, if you ever done any Lie group stuff. So this generalizes super cleanly to like any arbitrary Lie group. There's just a clean one-liner. It's like momentum, it's like momentum derivative, like L dot, plus like the omega hat equivalent for any Lie group is called this like adjoint thing. The adjoint thing times the momentum. That happens for every Lie group. So this is a special case where for SO3, the adjoint operator is the omega hat cross product thing. Cool. Fun fact. Oh, we were doing so well. Let's see if I'll have this back. I'm gonna keep my profanity to a minimum for YouTube. It's hard. It's hard. Okay, we're back. Okay. Cool. That's fun. Worth knowing about. Although in practice and robotics, like this is mostly all you care about. Although the filtering guys are really into Lie groups and stuff, and they make up new ones all the time. So maybe this is useful elsewhere. I don't know. Okay, cool. How are we doing on time? We have like 20 minutes, right? We can do this. It's going to work out. Okay, so this is the hard part of the whole thing. Roughly speaking, what we're going to do now is write down the big Lagrangian for all the links and whatnot, and just do this again. And it turns out what ends up popping out is this part shows up again, just like this, with all the mess. And then the rest of it, in terms of the joint angles, looks just like normal Euler-Lagrange. So we're going to write that out next. Not hard. And again, it'll be lots of glossing over details. I'm just going to give you the highlights. And show you the punchline. Okay, so we've got now we'll write this in general as L of Q comma V, and this is the stuff we've been doing the whole time, so this is no surprise, and we're going to have something that looks like this. So our big Lagrangian, the key thing is just that we've got V not equal to Q dot in there, right? And it's a special case of that here where it's specifically, we have a base link, it's got a quaternion thing and whatever, and the stuff we just did, right? Okay, so this is just expanding that out to like the general case where you have a bunch of joint angles tacked on the bottom. We do the same playbook. We're going to write down the least action thing with a constraint for the quaternion kinematics. And then the rest looks totally the same. So we got action, and it's that L plus this like momentum Lagrange multiplier thing, and then the quaternion stuff, which only happens on the base link. So this all looks exactly the same. That's why this is kind of easy after you do the single rigid body case. Okay, so that's just I putting the the knots on everything because it's the base link only. It's the only thing you have to worry about here. And then now if you look at this, right, we have the following variables. I guess what I'm really doing here is I'm splitting out the quaternion from the rest of the variables, right? And then this guy includes like the full pose with the asynclinal thetas, right? And this is the velocity we're used to dealing with. So what we do then is just diff this with respect to all the things. Okay. So the derivatives that don't involve the Q naught look normal, look like Euler-Lagrange equations, and that's easy. And you can kind of tell how that's going to play out. Like the second term just doesn't show up, right? When I diff respect to the other stuff. So, if I do this with respect to, say, the R naught, it looks super, super normal, like what we've seen in the past. So you get like partial L, partial R naught times delta R naught plus partial L, partial R naught dot delta R naught dot. We play our little integration by parts trick on the second term. So we flip the dot, so we get ddt partial L partial R naught dot, and we pick up a minus sign. And then this is what we want for all delta R naught, and then we pull out the Euler-Lagrange equation. So this is standard stuff. And I'm not going to do this for all of them, just rehashing, make sure we're all on the same page. Cool. So this is we'll lumber this 1. Then we can do the exact same thing for the joint angles. Looks exactly the same. We get the same Euler-Lagrange looking thing in terms of those. Nothing changes. We can do the omega, which is similarly easy to what we saw in the rigid body case. It just looks, the answer is slightly different. So we got delta with respect to the omega naught of this guy is going to be partial L partial omega naught minus L transpose all times delta omega naught. I don't have to do any integration by parts there. So the punchline there is that L equals grad with respect to omega naught of the Lagrangian. So that's the same thing we saw in the Euler-Lagrange case, or sorry, in the single rigid body case. It's just that this Lagrangian, I'm trying to be generic here, and that thing might include sort of other omega naught dependencies, maybe, right? So that's that. But if it doesn't, it then just looks like the standard angular momentum that we saw before, right? Cool. Okay, so the Q naught derivative is super messy, but it's exactly the same flavor of super messy that we just saw, not different. And so I'm just going to write the answer down. So the punchline is you're going to get something that looks like L dot plus omega cross L minus this thing. Can anyone tell me what this term is that I just tacked on here? So this is that omega cross L thing that we saw last time that's showing up. That's the sort of the term that comes from the big constraint, right? What's this thing? It's a grad, it's just a gradient of L with respect to a pose, right? in particular the Q naught, right? What is what does grad L with respect to a pose look like normally? It's like partial L, partial Q. We think about what that. It's like the gradient of the potential, and it shows, so it's a conservative force thing, right? So in this context, this is basically accounting for the fact that you might have a potential function that depends on the attitude, which is a real thing. Like you can imagine if I had like a torsion spring, trivially, right? You get that kind of thing to pop out. So this is the omega cross L thing that we had before. This is, because we're doing this for a super general Lagrangian here, this is the potential term that comes from having like a potential that's function of the attitude of the base link, right? Okay. There's that. And then what I'm going to do is plug in the definition of L to this guy. And then we're done. So I get ddt of. So I'm just like eliminating the L's from the thing like I did before. That thing plus this omega cross thing. And then this potential term, which is just using the attitude Jacobian there to like take us from like this quaternion gradient into the sort of gradient that we want. This whole thing has to equal 0. That is the punchline. Move this over a little bit. Okay, so this combined with the other equations is the full story. For floating base robots. So this gets a box. And we'll call this one number 4. So we have, oh, did I number the other ones? This is 1, this is 2, this is 3, this is 4. And I eliminated 3, basically, right? I got rid of it, so I didn't need it anymore. Okay, so then the story is equations 1, 2, and 4 combined, like stacked together, are the Euler-Lagrange equations for a floating base robot, where you have a base pose, with a quaternion in it, and then you have like joint angles for the rest of the links coming off of that base link. Something like that. Okay, so you just stack those and solve them all together. Some like random asides then, I guess. One is that this is like everything in here is like a special case of something, and there's like all kinds of fancy names attached to all these things. All of them, though, as you hopefully is more clear now, like all of these things are just, you do the least action thing, you make that look however you need to with whatever constraints you need and whatever variables you need to make it work. You just turn the crank, write down the derivatives, and out pop the equations of motion. That's the most general way of doing this stuff. All of these like first order necessary conditions for special setups of that with special choices of constraints and variables have different names and stuff. The last one I told you is like the Euler-Poincare, equation, and where you've got like a Lie group or whatever. This one, it turns out, is a special case of some two other things. So this thing is a special case of Keynes equations, which maybe you've heard of, right? So Keynes equations assume an affine kinematics relationship between V and Q dot. So this has that, obviously, right? So this is Keynes equations. But here we just did it for the specific case of like the floating base of the robot having weird stuff in the rest joint angles, right? So Keynes equations, general affine mapping, whatever. So fine. And then this is also a special case of another version called Hamel's equations, which are maybe the which allow you to have a general nonlinear mapping in the kinematics. and just turn the crank, right? Okay, so I guess if you wanted to like make some kind of hierarchy of these things, like Keynes equations, special case of Hamel's equations, this is a special case of both of them. And I suppose the Lie group stuff is kind of its own thing, but like you could also say Euler-Poincare is a special case of both these guys as well, whatever. But this is more than Euler-Poincare. This is more stuff going on, right? Okay, so that's that. This is basically this is the stuff we need for robots. So the rest of it, yeah, whatever. And then the last comment is we can write this thing down in the familiar manipulator form. That we're all used to. So this, basically just collecting terms and like labeling them as specific matrices. This is how I get to here. I'm gonna not write the gravity term as G because that's attitude Jacobian. That's annoying, and half the time you'll see that step into the C anyway, right? I don't know, or I can, and then I'll have to caveat it and say that's not the attitude Jacobian, whatever. This is the standard notation though in a lot of places, but you will also often see, and then I guess yeah, you might have like this is also terrible notation overloading because Jacobian versus inertia. This is really annoying. Okay, so this is the gravity or potential term, and then this is the Coriolis term. Often you'll see smushed together into one term that people sort of overload and call C as well, and they call it dynamics bias. You've heard of that? Whatever. There's lots of conventions here that are sort of have overlap and inconsistency. Yeah, that's supposed to be like your control inputs, and then you maybe have another. I guess I can use Y for that other thing. That's what we did last time, right? So this might be your like, Jacobian mapping, like any external forces on the end effector in, right, all that kind of stuff. So this is not the attitude Jacobian. This is potential term, aka like gravity. This is Coriolis term. And here, what's the Coriolis term? Well, so I mean, in general, there'll be a big one associated with the length too, but for the rigid body or the base, it's this omega cross, and L thing is the Coriolis term for the free rigid body and for the base, right? Fun. Mass matrix, which will pop out of that first term, right? And then this would be your like input Jacobian for your controls, or sometimes people call this the selection matrix, which makes no sense to me.
No, that's I said I don't.
Okay, that's good. Yeah, so this thing, input Jacobian, is what I call it. You maybe hear people call it selection matrix, which I think is a weird, dumb name. And then this Y thing, which is usually called J for Jacobian. There's too many Jacobians, and there's also the inertia to worry about. This thing is sort of the Jacobian mapping your external forces in. I don't know what that has another name other than Jacobian, but it's a specific Jacobian. Does anyone have a name for that? I don't know. But yeah, we talked about this before, right? It's the thing that would map, say, your foot forces on your legged robot into the generalized coordinates or whatever. Okay. And then the last note on this is that this is the more or less standard setup. Like this thing we just did today down to these like last equations, and then like massaging them into this manipulator form. This is the standard stuff in like all the robot simulators, basically. So Bullet, Mujoko for sure. Yeah, and the upshot is, we spent a lot of time deriving this mess, and this is why you don't do this by hand usually. That's why there's all these nice algorithms that do this for you. So you give the thing like a URDF file, and under the hood, it's going to like compute all those kinematics functions, build all these things, and then like take the derivatives for you. And there's been like decades of work on making this stuff fast. And there's all kinds of specialized fast algorithms for computing these derivatives and all these matrices, right? Featherstone, RNEA, ABA, you probably heard of some of these things, right? Okay, so you don't do this by hand in general. You can if you're a sadist and you really want to. Maybe for a special case, it's worth it. But generally speaking, use a toolbox to compute all this stuff for you. But this is if you wanted to write your own toolbox, that's like how it works. Okay, fun. I did have like a little code example of this that maybe I can get to work because we have a few minutes. I didn't think I was going to get there today because this was like a super gnarly day of math, but I was, I guess, faster than I thought. And this is annoying, but we can try. So anyone have any questions about this or anything in general?
So I'm curious, you talked about like generalized coordinates.
Yes.
And then maximal coordinates.
Yeah.
And like how this changes the maximal coordinates, right? Or do you actually write these equations?
Yeah, so this is a thing we're going to talk about some more, like literally next time. So generalized coordinates is just like literally saying any coordinates you want. So generalized coordinates is the physics word that just says like, basically where that's coming from is the whole idea that this whole like least action Lagrangian thing is coordinate invariant. So I can choose literally any coordinates I want. And those are generalized coordinates, right? In robotics, we typically refer to joint coordinates a lot, which are an example of generalized coordinates. But typically in robotics, when people say generalized coordinates, they mean these coordinates that we just talked about. So you can have joint coordinates and people talk about joint space, right? People also talk about minimal coordinates. That's a separate thing. Generalized coordinates and joint space and stuff don't necessarily have to be minimal. What minimal means is that you have a number of coordinates equal exactly to the number of degrees of freedom in the system. This is not minimal coordinates because I used a quaternion for the rotation part for good reasons. It's non-singular and doesn't do stupid things and blow up on me, but it's non-minimal, right? It's 40. And that's kind of part of why we had all this painful garbage. If I used Euler angles, that would be minimal coordinates here, right? And then when people say maximal coordinates, what they mean is that you basically, in robotics context, maximal coordinates refers to using the full SE3 pose of every single link all together. So when we did this kinematic Jacobian stuff, and I like mapped from my generalized coordinates with joint angles into that big thing that had the pose of every single link, those are the maximal coordinates. Yeah. Does that make sense? Cool. So yeah, basically in maximal coordinates, everything's easy. But you have to now explicitly enforce the joint constraints. That's the difference. So here, the problems are smaller, but they're dense. In the maximal coordinate context, they're much bigger because we're doing this full pose for every single link thing. And we have these explicit joint constraints we have to enforce. So they're bigger problems and they always have constraints. Here, we don't have any constraints, right? Yeah. That's the trade-off. So here, small, dense, unconstrained, maximal, large, sparse, constrained. That's sort of, and we're going to talk about this next time, and like fast algorithm stuff, which we didn't talk about yet. This is basically what like all these simulators, most of the current simulators use these exact, they're not exactly minimal, right? But they're close to minimal, and they're referred to as generalized coordinates. They're like joint angles plus the floating base pose stuff with a quaternion, right? That's what most of these guys use. There's reasons. We'll talk about the reasons a little bit more depth next time. So yeah, next time we'll talk about maximal coordinates versus minimal coordinate stuff, and hopefully in the last couple lectures get into like these fast algorithm things and like how they work and where they come from and whatever, that kind of stuff. That is the goal. And now we're out of time. I'll show you the code next time. Yeah, it's fine. We're done. I didn't like actually have it ready to go anyway. I gotta go find it. Anybody in Zoom land have anything?
Hi, Professor. I had a question about my project for after class.
Yeah, sorry. Can you say that again?
Oh, I just had a question for like my course project.
Yeah. We should probably have a little Zoom chat then. Are you around in general?
I'll be on campus at around 1 if meeting in person is better than over Zoom.
We could do
or
now if you want. That's fine. I'm gonna have to leave campus.
Okay.
To go to Squirrel Hill pretty soon. So let's just you're on the Slack, right? Let me clean up in here
Okay.
and go find a place to sit down, and I'll like ping you, then we can do a one-on-one soon.
All right, perfect. Thank you.
Cool. So give me like 10 minutes.
Yeah, no problem.
Yeah.
All right, see you.